Okay, so welcome everyone. Can you hear me good? Okay. I'm very, very pleased to introduce the PhD thesis defense of Hardik this afternoon. Thank you all for being here. So Hardik is one of my what I call pandemic students. He's joined the PhD program in the not so easy fall 2020. And despite all the adversity, he was able to do a pretty good job and be here today to defend his thesis, which is on online adaptation for safe control of constrained dynamical systems. And with that, I'll leave the floor to you. Okay, good luck.
Hey. Hello, everyone. Thank you all for coming to my defense. If my audio is not clear on the Zoom, please let me know and I'll try to adjust. So I will be presenting the work I did over my PhD on online adaptation for safe control of constrained dynamical systems. Oh. So autonomous systems are visibly playing a growing role in our lives. While initially we saw them in the context of more structured and highly tested environments like assembly lines, warehouses, or just aerial photography, now we are starting to see them out in the open. Autonomous cars, delivery robots, and concept ideas like social navigation and robots for service in hospitals and for taking care of elderly are becoming popular. However, a consequence of working in these new unstructured settings that are different, even in small ways, from the design phase, from the offline design phase, is that the performance of the system may degrade, and the constraints, for example, related to safety and collision, may be violated. A common solution therefore, is to make systems overly conservative. However, that not only leaves the task unfinished, but may also does not necessarily exclude a safety hazard. For example, we have seen all of these news reports in which an autonomous car stops because it's unable to find a path through the crowd. But that doesn't really completely eliminate the safety risk. Maybe it's safer than continuing to drive, but not completely safe. So uh, there are this is a very difficult task to achieve, and it has many aspects to it. For example, it's related to having how the robot perceives the world, how the robot interprets the world. But in this particular presentation, I will be focused on controllers, that is the algorithms the robot use to navigate physically in the environment. uh, in order to improve the capabilities of the robot, I will try to answer the following question: how to adapt robot controllers autonomously to remove the conservatism, achieve the task while still respecting all the constraints. So here's an overview of the roadmap and the objective of this presentation and my dissertation. My presentation will be divided in three parts. Uh, most of my presentation will be talking about a controller, which is simply a function that takes as input the state of the system, which can be, for example, position and velocity, and it outputs the control input, which can be acceleration or turn rate. In part one of the presentation, I will be presenting a generic algorithm to tune the parameters of this controller. The controller depends on some parameter theta, which, for example, uh, can define how aggressive or conservative my controller is in response to certain events happening in the environment. So consider this video over here, where I have a quad rotor, which is supposed to track the red path while avoiding the white obstacle. Initially, I start with some controller which is too conservative, and then my objective is to eventually adjust the parameters of this controller, which is the amount of repulsion force from the obstacle and the amount of attraction force towards the desired path, to be able to track the path as much as possible without violating the constraint. So now consider this scenario where we have a car which is trying to navigate through this track. It pings the controller to figure out how the future looks like. And these are the paths. Then I ask the controller to tune the parameters to improve the path. Okay, let me just run it again. Yeah. So now the controller tries to adjust the parameters, which is, as you see, the paths are getting tighter and tighter so that the car can go faster and navigate the area in less amount of time. However, this is like one of the solution in which we can optimize the parameters of the controller. However, this is a very ideal scenario, which won't really work in reality. The reason being, in reality, there are many things which can be different from the design phase. So for example, we can have uncertainty in the mass. We need not know the exact mass of the cars. It can occupy passengers with different weights. The tires have wear and tear with time, and so on. So what we would ideally like to do in this particular work is, instead of considering a deterministic future, we want to be able to predict a stochastic future, which means we want to be able to predict all possible positions of the car for a given control parameter. And once you are able to predict possible positions of the car, then we start optimizing the parameters and achieve at a good performing but safe path. The second part of the presentation, I will be focusing on a very specific type of controller, which is control barrier functions. It can be considered a subset of the first part, but control barrier functions are getting really popular. Control barrier functions basically define a filter in which, if my car is trying to go too fast, the filter will be like, no, stop, you are going too fast, you will collide with the wall. It's not actually a complete controller in itself, but it's only a filter. Now, issues arise when you have multiple filters acting on the system at the same time. These filters were defined in the offline phase individually without regard to existence of any other filter, but when imposed together, the problem can become infeasible with no solutions. And I will show that by tuning some parameters related to control barrier function, you can actually you can keep satisfying all the constraints simultaneously. In the third part of the presentation, I will try to adapt the controller in a little different way. Instead of considering parametric controllers, I will just say that the controller is unable to satisfy all the constraints, no matter what adaptation law it uses, and no matter what trick it plays. So the only solution in this case is that we start disregarding the constraints because it's impossible to satisfy them. In order to do this, I will define a notion of priority, which will be something like additive priority. For example, you want to satisfy as many constraints as possible, if not all. And that's how the presentation goes. So the first problem statement for this presentation is, I want to be able to predict uncertain future and auto-tune parameters for performance and safety. The second objective will be enable tuning of control barrier function based filters for compatibility of multiple constraints. And the third objective will be to decide which constraints to give up under the setting of additive priorities when the controller is unable to satisfy the constraints. One way to categorize the existing approaches is whether they are instantaneous. So these approaches look what's happening at the moment, and they make an instantaneous decision of what to do. These approaches are usually really fast and efficient. However, they lack in performance over long term, and they cannot usually guarantee satisfaction of constraints. The second set of approaches we have is optimal or predictive approaches, similar to the example about the racing car I showed you before, in which they predict future as a function of the parameter of the controller, and then they start optimizing the parameter of this controller to slowly shift the trajectory towards better performing paths. Another way to categorize the existing approaches is whether they are offline, in which everything is pre-computed. For example, the whole paradigm of offline learning falls here. Bayesian optimization is also a very common approach. The second categorization will be whether the approaches are online, which in the context of this presentation simply means whether they are fast enough to be computed in real time as the robot moves around. And finally, they can be a combination of offline and offline approaches in which they use some pre-computed data and adapt the remaining online. In part one of the presentation, I will be proposing an online approach, which is predictive in nature. So I mentioned that I want to be able to predict these possible positions of my robot, which is like a tube. And this tube won't be a hard boundary, but it will be a set of most likely states of where my robot can be in the future, which means I will be talking in terms of probability. And this is the notation I will be using, which is the state of the robot in the future at the next time step, t+1, is some function of the state of the robot at the current time step, and everything is stochastic. So Gaussian is a very popular distribution, which we commonly see in many applications. This Gaussian can also be 2D. It simply tells me that if I were to ask what is the most likely speed of the car that is most likely to be observed, it's about the center of this Gaussian, and so on. The distributions need not be Gaussian. We can have something much more complicated. A good thing about Gaussian distribution is that if I ask you what is the likelihood of observing this particular car speed, Gaussian distributions have a well-defined formula, which I can just plug in the value of that particular speed. I can compute the output of this formula, and I can tell you this is the likelihood of observing that particular speed. However, what if I were to apply a function to this position of the car, for example, x sin x, which is a very common function which appears even in many kinematic systems. In this case, then someone can ask, what is the formula I should look up to tell you what value of x sin x has what likelihood to be observed? And the answer to this question is there is no formula. Predicting future state distributions is known to be analytically intractable, which is it does not accept a formula like this, and you can only numerically approximate these expressions. So this is how you would compute the probability of future state. In this expression, P of xt is just how the current state is distributed. What are the likely positions of the car? This term over here is just the dynamics of the robot. Each system, each robot has its own dynamics, and you integrate it to get the likelihood of a position xt plus 1 at the next time step. This problem has been at the core of stochastic model predictive control as well as model-based reinforcement learning. One of the problems which has been at the core of stochastic MPC and model-based reinforcement learning. So before I proceed forward, I also want to introduce this simplification here. So I cannot keep drawing infinity going Gaussian distributions in every slide. So I will be just drawing these 2D figures, which look like an oval, which simply mean that maybe 95% of the times I am likely to find my robot inside this area. Other times the robot can be outside. So some common methods that exist in the literature for state prediction is successive reduction to Gaussian. So if we do have a non-Gaussian distribution of where my car can be, we approximate it with a single Gaussian distribution. This approach has been really popular, and every time we get a new non-Gaussian distribution, we immediately approximate it with a Gaussian, and we keep predicting the future. And that's how we obtain the tube that I was referring to in my video earlier. This method is not an approximation for linear systems. It's widely used in Kalman filters. For nonlinear systems, the most generic case that has been reported in the literature to my knowledge is a Gaussian process with a Gaussian kernel, in which again, the posterior or the output distribution will remain a Gaussian. It's a state-dependent Gaussian, but a Gaussian nonetheless. The second approach is Monte Carlo. In this particular approach, we maintain like 1,000 or 1,000,000 particles of the distribution of X by randomly sampling from the distribution of X. And we pass each of these points through the function x sin x to get the distribution of how the function x sin x will look in the future. This method, in theory, as the number of particles go to infinity, is probably the most accurate method. However, it's also computationally very expensive. So it's very rarely employed in real-time systems. When it comes to Gaussian approximation, it's really efficient and probably the fastest method, but it can lead to huge approximation errors. For example, this result, which I show here, this is the distribution of a mounted car problem in which a car is just going up and down the hill. And after predicting the future for a certain point, on the left is how the Monte Carlo distribution will look like of where the car, of how the velocity and the position of the mountain car is distributed. And on the right is how the Gaussian approximation think that the velocity and position of the car is distributed, which are very different from each other. In my research, I use a method called uncentered transform, which is like Monte Carlo. It will choose points to represent a distribution, but instead of randomly sampling from the distribution, it chooses points through some principle. And the principle is choose the number of points that best represent a distribution in terms of its moments. So for example, if I give you this distribution and I were to ask what are the two best points to represent this distribution, I will likely choose points which are symmetrically distributed about the center of the Gaussian. If I were to ask you to choose 3 points, maybe this is how many people would choose these 3 points. So in the first case, I would assign a weight of 0.5 and 0.5 to both the points because they both are sort of equally likely to happen. In the second case, I will assign a higher weight to the point in the center because it's more likely to happen and less weight to the points near it. So when I'm choosing these points, as I mentioned, my objective is to choose points that best represent the distribution in terms of its movements. The first movement, mean, which is commonly known as average. The second movement is standard deviation, which is the spread. So for example, the red distribution has a higher spread than the blue one. The third movement is the skewness, which is a measure of asymmetricity in the distribution and so on. And you can keep going on for infinite number of moments. So then the objective of this first part of the presentation is how do we best use these finite number of particles to predict future instead of Monte Carlo, in which we can use arbitrary number of particles. So here, let's say this is the initial distribution of the state. Instead of a perfect oval, I just drew an arbitrary curve just to emphasize that it doesn't have to be a Gaussian distribution. I represent this distribution with 5 points. Now, what previous works using uncentered transform was missing is that in real life, the uncertainty can be state dependent. So for example, you have this car driving over a dry and snowy patch of the road, or you have the quadruple example from before in which I have this fan running on the left-hand side, which is a localized source of wind disturbance in the environment, and therefore the effect of this wind will change with the position of the quadrotor. Furthermore, it's very difficult to model aerodynamic effects very accurately. So not only does the magnitude of wind disturbance changes, our estimate of the disturbance or the uncertainty in our estimates of how the wind affects the quadrotor also changes with the position of the quadrotor. So if we want to predict future under such a model in which the uncertainty is state dependent, each of these points will lead to a different set of future. And each of these futures will have different uncertainties. Some points will lead to higher uncertain future, some points will lead to a lower uncertain future. This is what I call the expansion operation. However, if I keep repeating this over multiple time steps, the method quickly becomes unscalable because the number of points increases exponentially. So in the next step, I propose a compression layer, which simply compresses these 15 points into the best possible 5 points. And the way I choose these best possible 5 points is again through the principle of moment matching. So I'm hoping that the mean, the spread, the measure of asymmetry of these 5 points is as close as possible to the corresponding moments of these 15 points. So for certain ways of choosing these points, we have really nice analytical formulas, which are also differentiable. And that is what I will be exploiting in my subsequent slides to devise an algorithm that can start tuning the controllers. So before I go to the controller part, here's just a verification or simulation of how my method behaves compared to Monte Carlo. So this is the dynamics of the system in which at each time, for a two-dimensional state X, I applied this weird looking function over here, which is cos of x1 plus, in which the mean of the Gaussian is a state dependent mean. And the mean is a cos and sine and cosine function of the state. And then the variance of the Gaussian is also state dependent. So this is how the distribution progresses with time. The blue particles are the Monte Carlo, about 50,000 Monte Carlo particles. And the yellow and the orange are using the proposed algorithm, but two different versions of uncentered transform. This distribution is called Excalibur distribution because it seems as if it's drawing a sword out of a flat stone, and I named it. So what's happening here, these are the snapshots of what's happening in this particular simulation. This is how the distribution progresses. So the yellow points are also using my algorithm, but they only try to maintain the mean and the covariance. They ignore the measure of asymmetry. Whereas the salmon-colored points also include the measure of asymmetry and therefore are better able to represent the distribution. If I were to do a time analysis of these different methods, for the Monte Carlo, we see that the time increases exponentially with the number of particles. The first bar over here is for Monte Carlo 500 particles, then 5,000 particles, and 50,000 particles. Compared to that, the proposed scalable approach is much more efficient. And if I were to stop doing compression operations, but only keep expanding the particles, in that case, the complexity is even worse than Monte Carlo because the number of points just keep increasing exponentially. So this is just to show that we do need compression operation because in real applications, we want the algorithm to be scalable and real time. Again, just to emphasize once more, just to introduce another note regarding Monte Carlo is that the accuracy of Monte Carlo drastically increases with the number of Monte Carlo points used. So the green curve along with the green shaded area you see here is the estimates from Monte Carlo using 500 particles when the procedure is run multiple times. So the shaded green area represents the standard deviation, which is every time I run Monte Carlo with 500 particles, I get very different results. This variation keeps getting smaller and smaller as I use more and more Monte Carlo particles, but at that point, it's not suitable for real-time application anymore, at least for a serialized curve. So before I proceed to how I tune the parameters of the controller, I just want to revisit how, as a user, I can use the predicted future to design a control input. So my objective here is to navigate from the bottom left to the top right. And I, as a user, can ask the controller to design a path that guarantees safety with 50% probability, which is I have 50% chance of colliding with the obstacle or not colliding with the obstacle. And this is the type of path I expect to see in return. I can also ask the controller to plan a path with 95% chance of safety, and this is what I would expect. The ovals here are what represent the 95% confidence interval of a distribution, which is my method thinks that the actual state of the robot is 95% likely to lie inside these orange colored ovals. And the blue area is a verification using 50,000 Monte Carlo particles. So in this case, my method does under approximate the actual distribution, but it's much more scalable and it's suitable for control applications. So now moving on to the control adaptation, I call my algorithm 4C. 4C stands for predicting future, but I also call it 4C because there are 4 different C's in this full form over here, which is 4C for certified constraint control. And again, the controller is something that takes the state as an input, for example, position velocity, and outputs the acceleration or turn rate. So I have a state X. I can compute the control input using my controller, and I can compute the next future state X2. And I can keep repeating the future to keep predicting I can keep repeating this procedure to predict more and more states in the future. And in this setup, each of these control input was computed using the same controller, which is phi of theta. So they share a parameter theta in common. The objective for me is to optimize the policy, which means I want to maximize some performance criteria over a time period. A standard way to define the performance criteria is that you define performance index for every time step and you sum all of them up. So that's what I'm doing over here, where small r is the performance index or criteria per time step. Now, if I were, so this performance index R2 can be computed as a function of the state X2. And then the way R2 is related to the control parameter is through all the edges that connect R2 back to the parameter theta, which is through the state X2, as well as going back to this control input U1. If there were no constraints in the system, I can simply exploit this relationship with well-defined formulas from my propagation scheme to simply do backpropagation, compute the gradient of the reward R2 in the future with respect to the parameter of the controller theta, and then move theta using gradient descent in the direction that improves the reward. However, I do have constraints in the system. So a gradient descent that solely focuses on improving the performance of the controller cannot ensure that the constraints can also be satisfied. So here I take inspiration from sequential quadratic programming literature, in which if the constraints are already satisfied, I try to find theta dot, which is as close as possible to the direction in which the reward or performance is improved. But then I immediately project it to the set, which also satisfies the constraint. So this projection here, in this case, is based on first order approximation of the constraint variable. Theta is the current parameter. This is the gradient of the error, and theta dot is what I want to design. In case that the current one of the existing constraints is not satisfied, I let go of my reward because performance is not important if my safety is not satisfied, and then I apply gradient descent to keep improving my constraint. And that's how I devise a real-time scheme, which if the system is safe, it can keep improving the performance while keeping safety. And if the system is going to be unsafe in the future, it'll let go of the reward, and it solely focuses on slowly shifting the trajectories towards safer and safer side. So next, I will be showing some experiment results. So this is a quad rotor in which the control input is the thrust, which is the force generated by the rotors of the quad rotor. This thrust is 3-dimensional. This is the standard dynamics of the quad rotor, which simply says that the quad rotor motion is governed by the thrust that the rotors generate and the gravity. Next, this is a very standard formula for geometric controller, which is a known stable controller for the quad rotor dynamics. It computes the error in the position and the velocity, and it generates a feedback based on these errors to be fed into the quad rotor attitude controller. But now let's say we have some wind disturbance in the environment. In my experiments, I simulate this wind disturbance using this axial fan over here on the left. Because of this wind disturbance, there is this unknown term, which we don't really know. So what we do in the experiments is that we move the quad rotor around randomly and in some predefined paths. We collect the data of the actual acceleration versus the commanded acceleration. We fed Gaussian process to learn the difference between commanded and the actual acceleration, and then we use it in our model to predict the future. And the objective then will be to use this learned Gaussian process to optimize the parameters Kp and Kv of the controller, which govern how fast the quad rotor moves in the environment, to optimize this performance criteria, where this performance criteria is designed to promote tracking of the reference path, which is the red trajectory over here. But at the same time, we will be using my algorithm to also ensure that it doesn't really collide with the white obstacle. So this is the video I showed at the start of my presentation. This is how my controller behaves initially. It is safe, but it is overly conservative, and it is unable to track the reference path well. With the proposed algorithm, it auto-tunes, and this is the end result that we have. So since my algorithm is based on gradient descent, it of course doesn't achieve this in a single iteration. This is how the experiment actually goes. It starts being conservative, and as the quadrator keeps making loop, keeps looping, as the quadrator keeps looping, slowly it gets closer and closer to the reference trajectory while also avoiding the obstacle. But it's also not always good because I'm using gradient descent. It carries the same disadvantages that all the gradient descent based algorithms have, which is first, it is sensitive to a learning rate of the gradient descent. I have no idea about how nonlinear my system is. So if I choose a very large learning rate, it may start violating the constraints, as you will see in the second loop of the quadrature over here. The second limitation, or I guess not exactly a limitation, but the second uncertainty about my method is that the solution may not be unique. So for example, initially the parameters are bad, so it is violating the constraint. Slowly, it converges to a safe solution in this third loop. But then in the fourth loop, it converges to a different solution. The difference between the simulation and the experiment still exists because although I fed Gaussian process on the trained, although I fed Gaussian process on the observed data of the actual versus commanded acceleration in the presence of these wind disturbance, this is a this is a 9-dimensional space or in which I have the wind disturbance that depends on the position, the velocity, as well as the attitude of the quadrator. So it is very difficult to collect enough data that represents all possibilities in the test time. However, the proposed method is still a way to quickly tune the algorithms in real time. Okay. In part 2 of the presentation, I will be focusing on control barrier functions, which are a very specific type of controller, and I will be applying some methods from part 1 to tune the performance of these control barrier functions. So going back, we have a controller that takes as input the state and outputs the control input. In control barrier function, we define a safe set through a function h such that inside the safe set, the function has positive values. Outside the safe set, the function has negative values. And on the boundary, the function has value equal to 0. And then we have some generic dynamics of the system, which is not really important here, but just I put the equation just for reference. And this is the statement of the control barrier function theorem, which is the set S is I will just read it through first. The set S is rendered invariant if H is a CBF, that is, there exists an extended class K function alpha such that supremum of H dot is greater than or equal to minus alpha H, and so on. So what this basically means is that I have a robot and I have a safety constraint to satisfy, which is, in this case, the rover should not collide with the wall over here. If the distance of the rover with respect to the wall is d, the CBF gives me a condition that puts an upper bound on the maximum possible approach rate of the rover with respect to the wall. So if the rover is approaching the wall at a faster rate than what this condition allows, it will ask it to slow down. In this particular condition, this factor 2 is something that requires me to know everything about the system. How fast the rover can move, how fast can it brake, if it is approaching the wall at an angle in a 2D space, can it make the turn in time to avoid colliding with the wall, which in a way means that I know everything about the reachability or reachable sets of this rover. So finding a valid factor 2 that works across all the scenarios for all different positions and orientations of the rover is not a trivial problem. And there are many algorithms to either find these in the offline analysis or tune them online. In general, I will just denote this parameter 2 as new, and I will focus on how we can design this new. Yeah, I forgot to mention the simulation, but what control barrier function does is that as the robot gets closer and closer to the boundary of the safe set, it will ask it to slow down or turn away, so that by the time it reaches the boundary of the safe set, it is not going outside. So finding this new is not easy, and it is also not unique. So for example, in this particular case, I show a robot whose objective is to navigate from bottom left to the top right while avoiding this obstacle. These are two different controllers. What this optimization problem here means is that I want to find a control input close to what the user asked me to, but at the same time filter it out immediately if it is not satisfying the safety criteria defined by the CBF. And this is like one possible resulting path for the equation that I wrote here. The green path that you see here that gets even closer to the obstacle is the same filter, but made more aggressive. I can also combine multiple constraints. So I can have optimization problems in which, again, I want to find a control input close to what user wants, but apply two filters simultaneously. So this is one possible path, and this is the other possible path. In the second green path, I give a higher parameter value 6 to the second constraint, which is the obstacle on the bottom, which effectively makes the second filter corresponding to the second obstacle less conservative and allows the robot to get closer to it. The second and third limitation I would like to mention about the existing CBF approaches is that first, it's only a filter. So it depends on how user defines the desired control input. And second, both the first and the second problem are made more complicated by imposing multiple CBFs together. So let's see an example. Here I have a robot whose objective is to navigate to the bottom left in the presence of some moving agents and in presence of some areas where the robot is prohibited from going. This is the dynamics of the robot, which is a car-like model, except that it can turn in place and it can only move forward. I define my controller, which is this popularly known as CBF QP, which is again doing the same thing. I have the control input that the user wants. So the x-axis is linear acceleration, the y-axis is angular velocity. So this is the acceleration and the turn rate that my user wants my robot to follow, which is also shows up in the objective function of the optimization over here. The green area over here, oh, I'm sorry, I just realized my pointer was not showing. Okay. Okay. So the green area over here is the set of control inputs that my filters think are safe. So for each filter, if the user chosen control input were to lie inside the green area, my filters would think the user is choosing a safe action. But if the control input chosen by the user lies outside the green region, it simply projects it to the green region, which is it's trying to follow whatever user demands as much as possible, while still ensuring that these conditions imposed by control barrier function are respected. And this is the nominal controller that in this particular case, the user chooses. I will go over it soon later. And this is a run of how the system behaves as the robot moves through the space. Okay, I'll just run it again. So as you can see, because the CBF conditions are state dependent, the green area changes with time, which means the set of allowed control inputs, which these set of control inputs are, in this particular case, the acceleration and the turn rate of the controller, which are allowed by the CBF conditions, change with time. So if the CBFs are sensitive to the user design control input, we expect this variation of how this green area changes to also change with changes in user controller. So for example, if I were to make the user controller even more aggressive, this is how the system behaves. So we see that in this case, the robot goes to the bottom and it collides with the obstacle. And the green area also simultaneously goes to 0. In the third case, the simulation that you just saw, I make the user controller even more aggressive. And in this case, the green area immediately goes to 0. Although in this case, the robot is physically safe, but because the aggressiveness of the user controller is not exactly compatible with multiple CBF constraints imposed together, the overall problem does not really have a feasible solution. So these are the three problems which I just mentioned. Finding new for the CBF, finding the parameter new for the CBF is not easy. It is also not unique. Second, it's only a filter, so it is sensitive to the reference control input. And third, the combination of imposing multiple safety filters together on a system complicates the above two problem even more. So the idea I started proposing in my PhD that instead of keeping this parameter new fixed, we can start adapting it online as the robot navigates through the environment. What this allows us is that for every possible safe trajectory of the system, we have a customized response of the controller, which is what I call rate-tunable CBFs. So initially, we had a system in which we had the constraint h dot greater than equal to minus new h, which is the filter that the CBF condition imposed. And then we have a state x that goes into the controller, and the output is the control input. This translates the new system in which we design a new policy that takes as input the state x as well as the parameter new, and it outputs the original control input which the robot needs. For example, the linear acceleration and the turn rate, as well as it also outputs the rate at which my filter should change its aggressiveness or conservativeness. So here's an example in which I have a green robot whose objective is to track the red leader and to keep it inside the field of view, the camera field of view, which is given by the orange shaded region. And preferably, the leader should be at the center of the field of view. So I have 4 different cases here, and I used a CBF controller to do this tracking. The CBF controller has 3 different constraints: a minimum distance constraint for collision, a maximum distance constraint for keeping it inside the field of view, and a maximum angle constraint to again keep it inside the camera field of view. So there are 4 different cases. In the animation on the top left, we see that I don't use any adaptation of the CBF QP controller, and there are no control input bounds. And it's able to keep the leader inside the field of view, however, not really close to the center of the field of view, which is the desired result. And the second, which is the desired performance. In the figure on the top right over here, I apply the proposed algorithm to slowly start adapting the parameters of my controller so that the follower is able to track the leader such that it is always maintained near the center of the field of view. In the animation on the bottom, in the animation on the bottom left, we now impose control input bounds with no adaptation, and we see that the controller immediately becomes infeasible, although the leader is still inside the field of view, but we run into the same issue as before, that is multiple filters applied simultaneously are no longer compatible. And then finally, in figure on the bottom right, we see that I again apply the proposed algorithm, and it is quickly able to adapt the parameters to keep the leader inside the field of view, but it is also able to learn that because of control input bounds, the follower doesn't really have enough actuator bandwidth to keep up with the leader's motion. So if it tries to focus on performance, which is try to keep leader at the center of field of view, it will fail to satisfy the safety constraints, which is to keep leader inside the field of view, and it ends up moving in a straight line. So in this particular example, the motion of the leader is stochastic, but the whole stochastic model is made available to the follower, and it was able to use the proposed algorithm of predicting the future, applying gradient descent, and adapting the parameters of the CBF QP controller. Another case study that I did in my PhD was related to multi-agent systems, in which we have different type of agents in the system. Some of them are cooperative, which share responsibility for safety. Some of them are uncooperative, which do not share responsibility for safety, but at the same time, they are not adversarial, which means they actively seek collision. Most of the previous works assumed to know the identities of these agents beforehand, which is which agent is uncooperative, adversarial, and cooperative, and then design customized control responses corresponding to each of these 3 different cases. Or they tend to treat all the agents in the same fashion, making it overly conservative. So for example, if this is my robot and this is the desired path, it observes an unidentified robot going to the right. This is what it would probably, this is how it would probably respond if it would treat this unidentified robot as adversarial. It will make its controller very conservative, and it will end up deviating too much from its path. Whereas if it knew that the red agent is only uncooperative, that it will not try chasing the green robot, but it will also not deviate from its own path to give way to the green robot. The green robot can simply slow down, let the red robot pass, and then continue onto its path, while minimizing deviation from its original desired path. So the idea I propose in this work that I develop a continuous trust factor rho based on the observations of how much the other agent is contributing to my safety metric. So safety is again defined in terms of barrier functions, and the contribution to safety is measured in terms of the ease of satisfaction of my CBF constraints. So this is my CBF constraint. The contribution to how my CBF constraint changes with time can be decomposed into contribution by the first agent, which is the ego agent I am designing the control input for, and the other agent, which is the agent J. So the first factor that goes into my trust factor computation is how easily I can maintain the constraint. So I can observe how much the other agent is contributing to this safety filter, to satisfying the safety filter. And I can compare this value to the best contribution my ego agent can make. And this difference tells me how easy was it for me to maintain this particular constraint. If it was really easy, then it means I can make my controller more aggressive and relax the CBF filters. If it was very difficult for me to satisfy this constraint, and I'm sufficiently far away from this particular agent, then it means I should get more conservative and avoid going closer to this agent. The other consideration I had in this trust factor computation is that I can also take into account priors on where the other agent is going. So for example, in this scenario illustrated here, both these scenarios contribute equal amount to the safety. The agent J1 is moving towards the agent I with 2 meters per second, whereas the agent J2 is not directly moving towards robot I, but the projection of robot J's velocity towards the robot I is still 2 meters per second. So instantaneously, as far as my ego agent, the blue agent is concerned, both of them make the same contribution to safety. But if I were to have a belief that agent J2 is going in the direction where it was supposed to go, I can choose to trust it more. Combining both of these factors, I design an algorithm that adapts the parameter nu of the CBF based on this trust factor. And here are some experiment results. So these experiments results utilize CrazyFly, which is like a small 30-gram quadrotor. I have 6 different agents. The green circled agents are the ego agents for which I design the control input. However, they are also unaware of each other's identities. The only thing they share in common is that they use the same CBF-QP controller. The red agent is an adversarial agent, which will try chasing the green agent on the left. And then finally, the blue agents are uncooperative agents that will just keep moving up and down. And the desired motion for my ego green agents is to move towards the left. So here is an experiment run with the default CBF-QP without any adaptation. So we see that the red agent is chasing the green agents, and the green agents end up going outside the experiment field, and they are unable to go to their desired location. Whereas with the proposed trust-based adaptation, we see that initially they are conservative, but slowly they realize by looking at the uncooperative agents that uncooperative agents are not chasing the green agents, as well as the red adversarial agent is not really fast enough to catch up to the green agent. Both of these observations allow it to slowly adjust the parameter nu of the safety filter to make it more aggressive and reach its desired position. So this is just a simulation run of the experiment I just showed. This was the constant parameter case in which the agents end up going outside the field of experiment, and this is the trust-based adaptation. And the right figure here shows how my trust varies with time. So here I show the variation of trust. The black and the green plots are for the ego agent on the top, the green agent on the top. How does it trust changes for the agents on the green agents on the bottom? So initially the trust increases because the top green agent goes to the right, but the other green agents don't really chase it. So it starts trusting in those green agents more. And then when it finally turns back towards the left to go towards its desired path, the trust decreases because as far as this green agent is concerned, the bottom 2 green agents are directly moving towards it, which leads to decrease in the trust over here. But at the same time, we see that the trust with respect to the adversarial agent constantly increases, although slowly. This is because it observes that although the adversarial agent is chasing the green agent, it's not really able to keep up with what the best case scenario that the green agent could have done. Okay, that brings me to the third and the final part of my presentation and the last chapter of my thesis, which is what if the given controller cannot satisfy all the constraints? So in the presentation so far, I proposed some methods to adapt the parameters to be able to satisfy all the constraints simultaneously for all times. But what if, even with all my tricks, I'm unable to do that? So the only solution then remains is we need to start removing constraints from the optimization because it's an impossible scenario for the given controller. If I want to remove constraints, it means I need to define some metric which allows me to remove the constraints. And in this presentation, I will be calling it as priority. There are different ways to define priorities, and I will be working under the setting in which we have additive priorities. So for example, we want to satisfy as many constraints as possible. No single constraint has absolute priority, but they might have weights or they might have equal weights. And what's important is the summation of those weights. So again, I have a controller that takes the state as an input and outputs the control input. These controllers are given by some optimization problem, which again, like before, they have some objective function, for example, to choose a control input that is close to what user wants. And then they have some constraints which filter out this control input. And the way we use them in practice is that we ping this controller at every time step. So at t equal to 0, the controller outputs something valid, and my system moves forward. At t equal to 1, we again ping the controller, and so on. And then we observe suddenly that at the 4th or the 5th time step, we ping the controller, and it suddenly returns infeasible, which is there is no feasible solution left for this particular problem. So then the question is which constraints to remove and how to remove the constraints. So I also make 2 different classifications of the type of constraints. From now on, I will be dividing my constraints into 2 sets. The first set is what I call as soft constraints, which the controller is allowed to remove. The second set of constraints are hard constraints, which the controller is not allowed to remove, and it must respect these constraints at all times. So the objective will be to start removing soft constraints to ensure satisfaction of hard constraints at all future times. So here's a motivating example that I will keep referring to in this last part of the presentation. I have a robot whose objective is to navigate to these ordered set of waypoints from 1 to 9. These waypoints are optional, which means the robot can choose to not go to any of these waypoints. However, it must reach the final target position by in a given amount of time. It must also avoid collision with the static obstacles. And then the shaded area you see here is a non-deterministic disturbance that the robot is subjected to. For example, the surface might be slippery. So if the robot thinks that going to that area, if the robot goes to that area, it will be difficult to control it, and it won't be able to come back out of that particular area to reach the final target position in time. It should drop that particular waypoint completely. So each waypoint is realized through a time-dependent state control input constraint. So a standard approach to solving this problem is that we simply relax the soft constraints by a slack variable. So what a slack variable does is that it tells the controller it is okay if you cannot satisfy the constraint, but then you must still try to minimize the violation. So in this particular case, it still tries to go to each and every waypoint, and before it knows it, it gets struck at a particular waypoint. Note that this is happening because I am using a given controller. I am not designing some optimal controller which will know for sure how to get out of a really bad location, or it will not know for sure that a location is definitely bad until it reaches there. In contrast to this, the proposed approach is that we completely remove the constraint. So instead of adding the slack variable, sorry for this typo here. So instead of adding the slack variable, we simply remove the constraint completely. In this case, it doesn't even try going to the last waypoint over here, and therefore it is able to reach the final red target waypoint in time. So when it comes to related work, like I mentioned before, instead of having, if I were to find the optimal solution, it could be framed as an infinite time horizon optimization problem with slack variables. And because it is infinite horizon, although it tries to minimize the violation, it will still ensure that the robot can reach the final target waypoint. The second most common approach is defining absolute priorities, which is not the setting I'm considering, but there are several papers which define that this is the most important constraint. So that reduces the problem to a hierarchical procedure in which a control input is designed to first ensure that it can reach the final target waypoint, and then it starts going backward, and it tries to also go to other neighboring waypoints as long as it can still reach the target waypoint in time. The setting that I'm considering is additive priorities, which has been a common topic of research in optimization literature outside of dynamical systems. So if I have been given an optimization problem which is infeasible, that is, it does not accept a solution, the objective is to remove minimum number of constraints to render the remaining problem as feasible. This problem is known to be NP-hard, which stands for non-deterministic polynomial hard problem, which means it takes polynomial time just to check if the solution is actually a solution. So that doesn't really tell me much. So hopefully this will help everyone understand, which is if I were to give you a Sudoku and I give you the solution of the Sudoku, how long will it take for you to verify that my solution is actually the solution? So in order to do that, you will have to plug in each and every value that I tell you, the minimum number of operations you will do is number of rows times number of columns, which is total number of cells, which is a polynomial number of the system parameters. Plus, you will also, after you plug in every value, you'll have to do some check going backward and seeing that the conditions are still satisfied. So since it takes polynomial time just to check if the solution is still a solution, it is expected that these type of problems take even longer to actually find the solution. Whether it can find solution in polynomial time or not is an unknown, is an unsolved problem. We don't really know if p equal to np, which is a polynomial time solution, exists or not. So the most common approaches to solving problems like these is to propose heuristics. So that is what I will be doing here. So just a quick recap of the system I have. I have a controller that I ping at every time step, and then I see that the controller suddenly becomes infeasible at some future time step. So we applied some existing algorithms of solving the NP-hard literature from the optimization literature into this type of robotic system. And these algorithms are also based on slack variable. So they include slack variable, but then they assign a score to each and every constraint, and the constraint with the smallest score gets removed, and they don't really perform well at all. And we realized the reason is the slack variables are non-zero only when the problem actually becomes infeasible. So in the time instance from t equal to 0 to t equal to 3, when the controller actually outputted something valid, the slack variables were 0 because the controller was able to satisfy each constraint exactly. It is only at t equal to 4 when the controller is not able to satisfy the constraint, that the slack or the relaxed parameter is non-zero. So then the question we started asking was, can the time steps t equal to 0 to 3 inform us about the structure of the problem at t equal to 4? Which is, because this is a dynamical system in which things change gradually, can we expect that the past can inform us about which constraint to remove in the present? So the proposition was the active constraints from the past are more likely to lead to infeasibility. So whatever constraints were actually guiding my safety filter in the past, they are also more likely to cause infeasibility in the future. So here is the same simulation in which I have a robot navigating in the presence of 3 obstacles. The green area is the set of control inputs allowed by all my safety filters simultaneously. And as the robot moves, we see that the red dot usually lies on the boundary of this green area, which means that most of the times when a robotic system navigates, the control input that is actually chosen, which is the red dot, is active for one of the constraints and not all the constraints. So in optimization literature, they have been dealing with static optimization problems with no correlation between optimization problem at different time steps. But we have a dynamical systems in which boundaries change gradually, and the solution often lies on boundary. So this time series of active constraint can help us inform the decision of which constraint to give up to prevent the green area from going to 0. And because this is an NP-hard problem, we believe that this prior is a good prior to have for NP-hard problem, which usually require non-polynomial time algorithms to solve accurately. The way we keep track of active constraints is very simple. It's simply given by Lagrange multipliers. So just a very brief overview, we have an optimization problem which can be converted to an unconstrained form using a Lagrange multiplier, or a simpler constraint form. The Lagrange multiplier is constrained to be greater than 0. And the KKT conditions of optimality tell us that the Lagrange multiplier is greater than 0 only when that particular constraint is active. It is equal to 0 when the constraint is inactive. And at the same time, it also gives us an idea about the sensitivity of the objective function to the constraint. So it not only tells us which constraint is active or is actively guiding the control input, it also tells us how sensitive is my final chosen control input to this particular safety filter. So the heuristic we propose is that we assign a score to every constraint based on the summation of Lagrange multiplier values over multiple time steps. And because Lagrange multipliers are non-zero even when the problem is feasible, this heuristic has non-zero score if even in the past time steps when the controller did output something valid. So going back to the same example, we use a single integrated robot in the example I'm going to show you here with the deterministic and known disturbance model, and each waypoint is achieved through a time-dependent state constraint, and everything is put together again in a CBF-QP formulation. So we compare different approaches. The first one is the slack approach, which was the baseline I mentioned before, in which we relax the constraint, but it still tries to minimize the violation. So it ends up going to the waypoint 7, and because of the slippage over there, it is unable to get out of that area in time and reach the final target waypoint. In the second approach, we performed an exhaustive reachability search. So we make a tree of all possible paths that the robot can take, and then find the shortest possible path which satisfies as many waypoints as possible and also reaches the red waypoint in the end. Third, we do an exhaustive search over reduced controllers. So I use the same CBF controller, an optimization problem with multiple safety filters. And at each time step of the simulation, I explore every single possibility of which safety filters I want to keep and which safety filters I want to remove from my optimization. So this is an exponential search. And this is the best case solution I got for a CBF-QP controller. So this tells me that the maximum waypoints I can hope to reach is 5 before I reach the final target waypoint. And the ideal would be to achieve this performance with the proposed heuristics. The next algorithm is the Chenix score. And Chenix algorithm is a standard way to solve this particular NP-hard problem in the optimization literature, which we then adapted to this particular problem. And we see that it performs very poorly. It is unable to go to any of the waypoints, and it simply drops all of them. We then apply the proposed score in a very specific way to decide which waypoints to drop, and it performs really well. It is actually able to go to 5 of the waypoints. We also proposed another variation of our algorithm, which uses the same heuristic Lagrange multiplier-based score, but in a more efficient algorithm. In this case, it performs poorly compared to the variation one, but it is still able to reach some of the waypoints. So here's a table, and I would like to emphasize. Here's a table of comparisons, and I would like to emphasize some key observations here. So because this is a heuristic, we do sort of a statistical analysis of how these different heuristics behave under different conditions. So we simulate the scenario for different number of waypoints, different levels of disturbance level in the environment, and we compare different methods. The reachability-based approaches, they take hours for us to compute on a computer. It's a naive Python code, probably can be done better, but this is what it takes us. For the exhaustive CBF search, in which we explore every possible combination of constraint at every time step of the CBF QP controller. Initially, for fewer waypoints, it performs really well just because the problem was feasible most of the time. But as we increase the number of waypoints, it again takes hours to compute the solution. The columns on the right side inside the blue dotted line are the results for the three heuristics. The two heuristics of these are using the Lagrange score, which is these two columns, and the middle column is for the slack variable-based heuristic. So we see that our method performs better than the existing, the algorithm that we adopted from optimization literature to a dynamical system like this most of the time. So in conclusion, I started this presentation with a method that predicts the state. And then it starts tuning the parameters of the controller to slowly improve how my future trajectories are going to behave. So this method was presented in chapter 5 of my thesis. So I didn't really go in the exact chapter order of this for this presentation. In the second part of my presentation, I focused exclusively on control barrier functions with an application to multi-agent systems. This is because control barrier functions are getting really popular, but there are several issues pertaining to control barrier functions when multiple safety filters are applied together. And I wanted to show that by adapting the parameters of CBF, we can circumvent some of these issues. And these have been included in chapter 3 and 4 of my dissertation. And finally, I wanted to start thinking about the question that what if the controller simply cannot maintain all the constraints? In this case, which constraints should we drop when under the setting of additive constraints, which is, for example, we want to satisfy as many constraints as possible. And this was included in chapter 6 of my dissertation. And this is the list of publications. And yeah, thank you so much. So I guess it's time for the emotional speech. So yeah, first, I would like to thank my committee members, Professor Panagu. We have been working together for almost 4.5 years now. I think we had a rough start due to COVID, like you mentioned. And I remember that we finally started meeting in person sometime towards the end of my second semester. And when I started meeting you in person, I was like, whoa. I mean, I can just take a pen, I can use the whiteboard, and we can just start interacting and writing together. And this is so much more productive than what we have been doing like for the past 7 to 8 months. Because I think at that time we were just not used to Zoom meetings and tablets and so on. So when I came here, I was far from being an independent researcher, and I had a lot to work on on my approach to solving a problem. And while my problem statements in the end, what I presented today turned out to be very different from what we initially planned for me, I think they were very motivated by your ideas on working with CBFs, as well as the topic of graceful degradation of constraints that I believe you have been wanting to work for years. It's been a long journey, and despite many challenges in work and personal life, I'm grateful that you kept with me so that I can reach this point, irrespective of whatever happens in the next 1 hour. Vasilis, I did your very first class in University of Michigan. I believe that was my second semester. And after that, we have maintained a good relationship. I think we kept meeting for meals, for playing with your pets. And thank you for sharing all the stories about your life as a researcher and as a professor to me. I think it was very interesting for me. And I'm also really grateful that you accepted to be in my dissertation committee. I did keep my distance a little bit after you were in my dissertation committee, so I hope there is no favoritism here. And then Ram and Nishmi, we mostly met in the context of my dissertation, but I also did both of your classes in my first and second years.
And actually, that's when I decided that I would like to have you in my committee. Initially, my hope was once I have you in my committee, I will also collaborate. But then it just didn't really work out. With my funding keeps changing, different expectations, and I didn't really get the opportunity. But thank you for being in my committee. I would also like to thank some of my collaborators. So I was fortunate enough to be funded by Toyota for 2 semesters of my PhD, as well as they also offered me internship for 2 summers. Daniel, Georges, Bart, and Hideki-san. It's been a pleasure working with them, and I think I learned a lot of them, and they have gone to different lengths to just support me and accommodate my request as much as possible. They have also given me opportunity to meet an amazing team of researchers from all over US, and I really enjoyed working with them. We also collaborated with Professor Ames and Ryan, who is, I think, the person I have met most in all of the conferences I have visited so far. And finally, some part of my PhD was also funded by ONR, and half a semester of a single semester was also funded by General Dynamics. We didn't publish any paper, but I'm still grateful to them. And it was really interesting ideas, which I believe the junior students from my lab are going to follow up in the future. I would also like to thank all the robotics staff. I think the department wouldn't really be the same without them. When I talk to my friends from outside robotics, the first thing they usually mention, oh, like Damon is so nice, or Kimberly is so nice. Like whenever they want to collaborate with the department or have any work, any management related work, these robotics staff is always available to help them. And I think I don't need to tell how much robotics students appreciate the robotics staff over here. I would also like to mention, so over my PhD, I was in some organizations and clubs. So the first one, which is RGSC, I think it was really interesting for me to be in a student organization for the first time. I think my tasks were mostly very simple. In the first year, I was secretary, so I just had to, take meeting notes, schedule room reservations, which Andrea, being the president, she liked to do everything by herself, so I didn't even really get to do that. And I would just go enjoy the meetings, enjoy how they would discuss the student issues, plan events for the students to improve the involvement of the student community. So yeah, it was really fun. So I think I worked the least, except for the 4 months when I was also the geo steward. That time, I think I worked the most of anyone in robotics. If someone doesn't know, it was a time when geo went on a strike, and it was a lot of work for me because I just had to communicate between different GS and the geo. In my final year, I also needed to vent out and maintain my sanity. So I I joined Title Boxing Club in Art Corner Studio, which really helped me. And yeah, just doing a free promotion for them here, and really good places to go. So before I go to the more emotional part, I wanted to share some other experiences. So I have really enjoyed the conferences. I think my first conference was in ICRA. That was the first in-person conference after COVID, and so many people came. It was a super spreader for COVID. And I think for me, it was a turning point because before that, I was really struggling with my PhD, but the feedback I got from the researchers in ICRA and the way they appreciated my work really encouraged me to keep working in this particular direction. So overall, really good experiences going to all the conferences. But one of my friends also mentioned once that I might be cursed when it comes to going to the conference. So in ICRA, I had a tailbone injury. And I was so excited that I just moved all over the place for the first 2 days of my conference. And by the third morning, I couldn't even move. And I had to go to emergency care. They gave me a painkiller, and that's how I gave my presentation in the evening. And I often joke to people that even if you don't like my research, I won't feel anything because I have painkillers, so that's fine. Then I went to L4DC. There was a forest fire. So they ended up moving the conference from Stanford University because there was no power in Stanford University to a Palo Alto community house, which also turned out to be nice because we were presenting poster papers. I was not presenting, I was just visiting, but people were presenting poster papers next to a swimming pool. My next conference was IROS 2023. I volunteered and I was driving there in the morning, and I ended up going to Canada by mistake. And I just didn't go by myself. I took 6 more people with me on a University of Michigan van owned by Regents of the University of Michigan. The Canada side was super chill. They didn't really care about it because this is a mistake that many people do very often. Because once you miss the last exit, you have no option but to continue onto the Ambassador Bridge, cross the bridge, and then come back. The issue was we were international students with no passport. Some of us only had a student ID cards, and one of us had his preferred name, not even his actual name. They still let us turn around in 5 minutes. The US immigration held us for 3 hours. And we never reached to reporting for our volunteer duty. In the next conference, which was in Cancun, I lost my glasses pretty early in the conference. So my whole experience of Cancun was like a 480p movie, which I can't really even tell if it's as beautiful as I thought it was or not, or even more beautiful perhaps. The second one, which is ACT 2024, which was in Toronto this year, I hurt my wrist and it took me about a month to heal it. And then finally, of course, the biggest conference of all, my PhD defense. Last week, I had a car accident. And yeah, this car accident happened literally 2 weeks before my lease was ending. My lease is expiring coming Monday. My airbags went off, the insurance took the car, and today they decided that it's a total loss and I will never get it back. But yeah, and I'm here on ibuprofen. So hopefully after the defense, I can just rest at home, give my legs a rest so that it heals in time. So next, I would like to acknowledge the people who have contributed to my life and especially the PhD experience so far. So I'll start with some family and old friends. So this is my mother on the left, my aunt on the right, and my late grandparents. I'm really grateful for all the care that they have done for me, and especially the sacrifices that my mother and aunt have done so that I'm able to be here and work on my PhD. I would also like to thank my childhood friends in the photo shown above. They really like to pose for photos. They are still living in my hometown, and whenever I have issue or whenever I go back hometown, they make sure to hang out with me and support me. Finally, Farhad and my two of my friends from masters, although we are living really far apart now, they make sure to communicate with me frequently and like support me. Next, I would like to thank all the lab members. So Kunal, Vishnu, and James, we didn't really have a lot of time together. It was COVID, so we didn't really meet a lot, but I'm still grateful for the initial insight into your research directions that you gave me. And I think that helped me get on track to managing my different research projects and also cope up with the courses and everything else. Mitchell and Joseph, we did share a lot of time together and I really enjoyed my time with you. We had a lot of discussions and it has been really insightful in doing my research. Dev and Alia, we started the PhD experience together in COVID. I remember that 3 of us just used to meet because there was no one else to meet. We were like either do homework assignments together or do research together. And I think that's what really saved us from the seclusion that COVID put us all through. Panagiotis, who was a visiting student in our lab, but he started PhD almost the same time as us, so I'm just putting him together with us. Then we have had some junior students. Caleb came 2 years after me, and he has been a really good friend. We have had many new students recently, and I would say the lab is much more fun after all of them are here, so thank you for choosing this lab and coming here. I think in my first year, I used to think that the most number of people I would find in the lab is 4. Like it's a very lonely lab, and now there is no shortage of people in our lab. These are the 2 master students, Ray Yang and Albus, who actually contributed a lot to some of the things I showed you today. These are some other master students that have interacted with me a lot, and some of them also work with me, and some of them have contributed to the robot architecture in the lab that I used in this presentation. And finally, we have also had postdocs, and again, the same thing. I think the lab is more fun with all of you here. Because I did internship with Toyota for 2 years, and it's a research institute, for me, it was as having a different PhD lab, and I also had really good experiences. In 2023, I had 4 other fellow interns. In 24, I had 3 other fellow interns. And I think we developed not only good professional connections, but also bonds that will last a long time. I know most of these interns are actually online, attending my defense remotely, and one of them is actually here in person because he lives in Ann Arbor. Okay. So next, there are many friends here who have supported me, and I've had fun with them over the last 5 years. So this list is not at all exhaustive. I just wanted to highlight some photos which are important to me. So I'll just go over them quickly without like really mentioning through a lot of going individually to all of them. I would like to express my gratefulness to some friends in particular. I'll start with my housemates. My very first housemates, Joseph and Angie, we lived together for almost 2 years. They got engaged when they were living with me, and I think that was 3 years ago, but the memory of them getting engaged and the whole sang my housemate song and how it went is still fresh in my mind, and I think I will never forget it. My second housemate, he taught me a lot of Chinese cooking, and he was my only partner in going to badminton like religiously every week. I never got anyone else after him. My third housemates, Kelly and Sihan, I think it's been really fun living with them. And I think both Kelly and I found each other, like both Kelly and I couldn't have really found a better housemate. We share passion for Japanese songs, Russian-based songs. We go bicycling together, and we both are like gadget nerds. Next, I would like to thank Laura, Brian, Dave, and Shashank. So I think Laura, Brian, and Shashank have been the longest constant in my PhD life, almost from the start till the end. And I guess this is something that I'm fine having a fixed parameter and do no adaptation whatsoever. Dave, I didn't speak about you much before because you were gonna reappear in this slide anyway. I think we have had a lot of experiences together, not just with Laura, Brian, and Shashank. I think although we only share one paper in common as co-authors, much of my research progress has been possible because of having discussions with you or having you help me debug my code. And it's been really a pleasure working with you. And of course, same for personal life. Caleb and Susan, they are probably one of the newest additions to my group over here, but they quickly got close to me. And Susan was the first person to tell me that she already booked a flight to come here in person and attend my defense just for a day. So thank you for coming here. Michelle and Samantha, I think my second year of PhD was really special because of them. We were really close. We used to do activities together, and both of them supported me a lot. So I'm really grateful for that. Honor, so, oh, there you are. So yeah, thank you for all the movie and meal nights that we have had together. It's always fun to go out with you. Next, I would like to mention some people who, all these people have also supported me, but these remaining friends in particular have frequently contacted me over the past few months and have discussed my issues as if it was their own issues. So first, Jay, he has known me since my undergrad, like, I don't know, almost 10 years or so, and he's here just for a day to attend my defense. Thank you for coming here and supporting me all throughout this time, regularly contacting me. Second, Osgun. Osgun and I met this summer in Toyota internship, not in our research lab, but surprisingly, we just got really close really soon. And she has done a really good job communicating with me frequently, expressing her support and giving me suggestions on how to deal with all the life issues. And I'm really grateful for that. Second, Niba and Mark. So thank you for, I don't know if either of them are here, so Niba is here. So yeah, thank you for having me as part of your life. Thank you for taking me to food, to beauty parlors. Mark for inviting me to all your fun activities with friends. Tanner was one of my closest friends who graduated as a master, so he left me pretty soon. But he has always been there for me as a backup controller. So no matter what happens to me, I can like always just go back to him and expect that he will just listen to me. And finally, Youngsun, who has done an awesome job in the last few months of regularly checking up on me and never letting me feel that I'm doing this alone, and motivating me to improve myself and keep doing these things. And finally, all my lovely pets. So Shiru, Kong, which I had with my first two housemates, Jester, which I guess I have with Laura and Brian, Pippi, which I have with Sihan, Kobe with Youngsun, and finally, Luna and Jester, who for the past few months have been really nice. And whenever I work at home, they just politely wait for me to finish my work so that I can just play with them in the end. Right. Thank you.